Hello students, in this video I am discussing about compoundings of steam turbines. Okay, so it comes under module 3 of turbo machines. Okay, so coming to compoundings of steam turbines, it is only one stage comprising of single nozzle and a single row of moving blades. Okay, so it is used then the flow energy or a kinetic energy is available at inlet of the machine is not absorbed fully, okay, by one row of moving blades running at a half of the absolute velocity of a steam entering the stage. Okay, because the even for the maximum utilization, that is u by v is equals to psi, right? That is half. Okay, so it means to say that due to a high rotational speed, all the available energy at the inlet of machine is not utilized, which is being simply wasted at the exit of the machine. Okay, so also we know that the maximum utilization exit, the velocity of a steam should be minimum or negligible. Okay, hence for a better utilization, uh, one has to have a reasonable tangential speed of a rotor in order to achieve this. Okay, so we have to use two or a more rows of moving blades with a row of stationary blades between every pair of them. Okay, so now the total energy of the steam available at inlet of the machine that can be observed by all the rows, okay, in succession until the kinetic energy of the steam at the end of the last row becomes negligible. Okay, hence compounding can be defined as the method of obtaining the reasonable tangential speed of a rotor for a given overall pressure drop by using more than one stages. Okay, so compounding is a necessary for a steam turbines because of the tangential blade tip velocity greater than 400 meter per second. Okay, so then the blade tip are subjected to tangential stresses. Due to this, utilization is low, hence the efficiency of the stage is also low. Okay, so the compounding can be done by the following methods, that is namely velocity compounding, pressure compounding, or a stage, and third one is a pressure velocity compounding, and the fourth one is impulse reaction staging. Okay, so as you can see from this figure, first one is a velocity compounding impulse turbine. Velocity compounding, that is the greatest stage, okay, of a impulse turbine. Okay, so here it consists of a set of nozzles, rows of moving blades, that is rotor, and rows of stationary blades, that is stator. Okay, so as you can see from this figure, that is 6.3, right? That is velocity compounded impulse turbine. Okay, so it shows that corresponding velocity compounding of a impulse turbine, the function of a stationary blade is direct the steam coming from the first moving row to the next moving row without appreciable change in a velocity. Okay, so all the kinetic energy available at the nozzle exists successfully absorbed by all the moving rows, and the steam is sent from the last moving row with a low velocity to achieve the high utilization. Okay, uh, the turbine works under this type of compounding stage is called as a velocity compounded turbine. Okay, so for example, uh, Curtis stage steam turbine. Okay, this is the example for velocity compounding. Okay, so next we move on to pressure compounded impulse turbine. Okay, that is a rotate stage impulse turbine. Okay, so in here a number of simple impulse stages arranged in a series is called as a pressure compounding. In case of this turbine, turbine is provided with a rows of a fixed blades which acts as a nozzle at the entry of each rows of moving blades. Okay, so the uh, total pressure drop of the steam does not take place in a single nozzle, but divided among all the rows of a fixed blades which acts as a nozzle, okay, for the next moving blades. Okay, as you can see from this figure 6.4. Okay, pressure compounding leads to a higher efficiencies, because very high flow velocities are avoided through the use of purely convergent nozzles for a maximum utilization of the absolute velocity of a steam at outlet of the last rotor must be axially directed. Okay, it is usually in large turbines to have pressure compounded or reaction stages after the velocity compounded stage. Okay, so this is about the turbine pressure compounded impulse turbine. Okay, so next we move on to pressure velocity compounding. Okay, so in this method the high rotor speeds are reduced without sacrificing the efficiency or output. Okay, so the pressure drop of the from the chest pressure to condenser pressure occurs at two stages. This type of arrangement is popular due to a simple construction as compared to pressure compounding steam turbine. Okay, so the pressure velocity compounding arrangement for a two stages is, as you can see from this figure, that is 6.5, right? That is pressure velocity compounding. Here here the first stage and the second stage taken separately are identical to velocity compounding consists of a set of nozzles and rows of moving blades fixed to a shaft and rows of the fixed blades to a casing. Okay, so the entire expansion takes place in the nozzle. Okay, so the high velocity steam parts with only one portion of the kinetic energy in the first set of a moving blades, and then passed into a fixed blades where only change in direction of a jet takes place without appreciable loss in a velocity. This jet then passes on the other set of moving vanes where further drop in kinetic energy occurs. This type of turbine is called as a Curtis turbine. Okay, so this is about the pressure velocity compounding. Okay, and the last one is uh, impulse reaction turbine, right? So here in this type of the turbine where the application of the both principles that is namely impulse and reaction. Okay, so this type of the turbine, so as you can see from this figure number 6.6. Okay, the fixed blades in this arrangement corresponding to a nozzle is referred in impulse turbine. Instead of a set of nozzles, steam is admitted for a whole of the circumference. In passing through first row of fixed blades, the steam undergoes a small drop of pressure and velocity increases. Okay, so steam then enters into a first row of moving blades. As the case in impulse turbine, it suffers change in a direction and therefore momentum. Okay, so this gives the impulse to the blades. The pressure drop during this gives rise to a reaction in the direction opposite to that of added velocity. Okay, so this thus the driving force is a vector summation of the impulse and reaction. Okay, so normally this turbine is known as a reaction turbine. The steam velocity in this type of turbine is comparatively low, and maximum being about equal to blade velocity. So this type of the turbine is very successful in practice. It is also called as a Parsons reaction turbine. Okay, so this is about the compoundings of steam turbines. Thank you.